Okay, so in the previous video, I've talked about PCD and IVC and this pre-proof composition thing, and I've said that PCD is sort of like this like general proof composition thing, but IVC really focuses on recursion, and hopefully that made sense. And now I want to talk about this Sangria thing, which is pre-proof composition. And why do I mean by that? Well, remember when I said that you can do these kind of trees of proofs or let's say succession of proofs. The problem when you do recursion like that is that every step of the way, every time you create a new step, in your computation, you will have to create a proof from the previous step and verify it in this step. The creation of a proof here is actually pretty heavy. In general, in proof systems, creating a proof is pretty heavy. And so you're paying the cost of creating a proof at every step of the process, which is kind of costly and it's not necessarily very nice. It's very powerful, but not necessarily very nice. This pre-proof composition, which is really pre-proof recursion, because pre-proof composition is kind of hard, is that we kind of avoid this overhead. We're gonna say at every step of the way, I'm actually just going to recurse without creating a proof. And only at the very end, whenever I want to actually create a proof because it's useful in my system or something like that, like I want to like some verifier is interested in knowing um, the state of the computation at this point, then I can create a proof and I only pay the cost once. And so this is sort of the idea behind Nova. But when Nova came out, it came out for the R1CS arithmetization, which is not used in Plonk. And since I mostly talk about Plonk, which is the state-of-the-art proof system, I'm not super interested in Nova. Good for us, fortunately for us, Sangria came out a week ago or something like that, and it basically made Nova work for Plonk. And so I'm going to start talking about Sangria, which is really just a component of Nova, which doesn't really tell you how to do pre-proof recursion. But once you understand Sangria, I'll talk about Nova and how pre-proof recursion is obtained in Nova, um, and that'll make sense. So that first video is going to be focusing on Sangria. It might not really make sense, but once we're past that, I'll explain Nova and it'll make more sense. So what Nova said is that, okay, let me create a new page. What Nova says is that to do this pre-proof recursion, we need one primitive, and that primitive is called a uh, folding scheme, if I remember correctly. And a folding scheme tells you that you can pretty much fold a witness. And so maybe I should go back and then let's talk about that first. But we need to understand what's an instance witness pair. Or maybe I should write that as a list, but okay, let's keep that as a vector. If you remember correctly, in Plonk, you have these sort of things where you have a circuit and then you compile that, or that's the setup, which is deterministic. There's no trusted setup, or there might be a trusted setup at some point, but let's not talk about that. And that gives you the prover key or prover index and verifier key or verifier index. Doesn't really matter. And then if I want to prove something, I can take the prover key. I run the circuit with some public input or private input, some bunch of inputs. I get an execution trace. My execution trace is pretty much a witness. It's like all the temporary variables and values that were recorded as part of my execution. I give that and the prover key to a prover. And actually, usually you also give some public inputs. Uh, and public inputs came from this input. This input had the private input and public input. So public input is the same here. And that thing creates a proof. that doesn't make sense, again, pause the video and make sure that the compilation step makes sense, the execution of the circuit makes sense, and the prover makes sense. Now the verifier can take the verifier key and put that into the verify or verifier algorithm along with the proof, along with the public inputs, and these will return, true or false. And that's all there is to the API. And so in this API, let me choose a nice color. Or maybe yellow is too close. Let's choose some pink. In this API, we can think of the witness here as the execution. Actually, can I? Oh, yeah. This execution trace here, the witness, is this thing here. And if you remember correctly, in Plonk, it's like A, B, C, like the left, the right, and the output vector, like they're vectors. And the instance is usually thought of as the public input. So do I have some nice color here? The public input here that we use to run our circuits, and we used in the prover and the verifier, right? Is this X here? That's the notation of Sangria and of Nova, I believe. This X is just a vector of it's your public input vector. That's it. So so now we agree that's the API of Plonk, right? Our folding scheme says that there exists something that it's a protocol between a prover and a verifier that takes two instances witness like that and fold them into a single one. So imagine you have x1 w1 and x2 w2. Our folding scheme is going to fold that into a single, let's call that x3 w3. And it's this new thing is going to be the same size as this instance or this instance, and keep in mind that they're all for the same circuit also. That's very important, right? Because well, it's just very important. So the nice thing is that we with this folding scheme we compress two instances with two instance witness into one instance witness of the same size. So now we only have to deal with one of them. It's a very powerful thing that's sort of used all over the place in zero-knowledge proof systems. For example, the inner product argument uses something that looks very similar to that. And you'll see later in this video, I'll talk about IVC and PCD, and I might talk about the Halo protocol, and it's also using something very similar to that. And as usual with all these protocols that end up compressing two things into one thing, it's always the same trick. You have the prover that commits to some stuff, the verifier sends a random value, and then the prover does a linear combination using that random value. And so here, the natural thing is that the prover will basically do pub1 plus r pub2, so like a linear combination of the public instances, and the witness will be basically a1 plus r a2, b1 plus r b2. That's the new one, right? Hopefully that makes sense, etc. And the verifier can do the same, but with commitments. So the verifier will have access to like, this is the notation used in the paper, where everything is a commitment. So here you have well, public doesn't have to be a commitment, but it could be, but let's say it's still a vector actually. But W2 is, well, let's keep the bar. But W2 is a commitment to a commitment to B, and a commitment to C, with whatever commitment you're using. And here you can use the same commitment we're using for like polynomial commitment schemes, and pretend that the values in these vectors are coefficients if you want. In any case, the verifier does the same thing on their end, and they will obtain, pub3 equals, so here let's say they use vectors, but for W3, it will be the vector of A1 plus R times the vector A2, not the vector, the commitment, B1 plus R B2, and that creates a new commitment. So that's really the idea behind ANOVA and Sangria, is that you can take a linear combination of that, of two instance witness. So you haven't really proven anything, right? You've just, like, these two things are just like execution of the same circuit, but with different inputs potentially. And you're saying, I don't need to prove these two things independently. I just need to prove this thing of the same size, which basically is a linear combination of these two instances. And it's a random linear combination, so it's very hard for me to cheat. Basically, that's the idea. Because I did this protocol with a verifier, um, um, or if I want to make it non-interactive using Fiat Shamir, I did it with myself, but nonetheless, this thing here is equivalent to like checking both of these things, but it's the same size. So that's the whole idea behind the following scheme. So can I easily delete the right parts? Let's try. And before I delete the right part, then the idea is that you end up proving this in your proof system, right? Using Plonk, you end up proving that with the Plonk equation that like you have a polynomial that has roots in 0 or whatever. But instead of proving two separate statements, you only prove one statement. So you have a single proof. Okay, I'm gonna delete the right-hand side. I keep that part. I'm gonna be honest here. I'm not sure how to delete this. Yeah, okay, I did it. Okay, so both Nova and Sangria just realized that this actually doesn't work. So this is, doesn't work. But they realized that if you relax the Plonk equation, which is, okay, I'll remind you what the Plonk equation is. It's like QL times A plus QR times B plus QC times, QO times C plus QM for the multiplication times AB plus QC equals 0, right? We're trying to prove that, plus a permutation, but the permutation actually doesn't change. So that's, that's nothing about the permutation. That's the Plonk equation. But they realized that if you actually have random linear combinations here in these vectors or commitments or whatever, then it doesn't work anymore, right? If you substitute with what you obtain after doing our previous folding, then you obtain something that doesn't work anymore. For this thing, it's going to be okay because we're going to get QL A1 plus QR B1 is going to continue, and then we'll get also R QL. Oh, here it should be A2. A2 plus QR B2. Like this looks okay. This looks like a random linear combination of the two Plonk equations. But once we hit the multiplication here, we're gonna have some cross products. Actually, if you want, I can write it down. QM times A1 plus R A2, B1 plus R B2 will give us something really weird. We'll have, I can expand it if you want, but we'll have A1 B1. That's fine, right? But then we'll get R A2 B1 plus B2 A1 plus R square A2 B2. And so actually, you notice here that the the squares are not at the right position. It's A2, B2. So you notice here that this is what we want for the second equation, and this is what we want for the first equation, but we get some cross terms that are kind of annoying. And also notice that the QC will only work for the first Plonk equation, but there is no R times QC for the second equation. So what we really want is something that looks like the first Plonk equation for A1, B1, etc., plus R or R square, because here we have R square, or something, times the second Plonk equation for, actually let's write it here, Plonk equation for A2, B2, C2, right? And here Plonk equation for A1, B1, C1. That's what we want, linear combination of the two Plonk equation. So they say, okay, this doesn't work, but we can actually relax that equation. That's what they say, actually, relax. And instead of checking this equation, this Plonk equation, we'll check this Plonk equation instead. So we have a relaxing factor called U, and then same beginning. These are the monomials of degree 1. And then we'll have a multiplication outside of the multiplication with the relaxing factor U, QC. So that's sort of like the normal thing. And then we'll have some error term. Okay, so actually I should have written that in color so you can see the difference. But now we have what we call the relaxed Plonk equation. Just a note on the permutation. The permutation won't be affected. The permutation is still going to work because now the intuition is that you're checking if two cells are equal, where the values are like A plus R A2, A1 plus R A2, and let's say B1 plus R B2, and so we're still checking that A1 equals B1 here and A2 equals B2. Maybe I should have chosen different name, but that's the wiring between two different cells. Imagine that. The random linear combination is not going to affect that. It's still going to make the permutation work. So that's the intuition. But the Plonk equation needs the relaxing. So this is the relaxing, where we set U equals to 1 and E is a vector, by the way. E equals to the 0 vector at the beginning. When it's your first instant witness, you haven't folded anything, so it's fine. But once you start folding things, you will see that U becomes U1 plus R U2. You will fold the U, and E will become something that I'm not going to write, but basically it will cancel these cross terms that we have here that we really don't want. And so you'll have to write some vector that cancels that. And the intuition there is that your E is formed by multiplying R with like some vector. Actually, they call it T. I think it's like E1 minus RT plus E2. I actually don't remember exactly what's the equation, but maybe like that. But what matters is that they actually reintroduce QC times R square for the second Plonk equation. That happens modulo. Sorry. That happens multiplied to R square. And yeah, because we have the multiplication here at R square. I'm not sure. Yeah, I mean these are just intuitions. You can look at the paper to sort of see exactly how they compute that slack vector or error. But basically they make sure that the prover doesn't make doesn't do anything they want, and so the verifier will sort of also create like a commitment. They call it big E, but it's a commitment to E. Is like the commitment of E1 minus R times this commitment T that the prover can control, because we multiply by R, so it doesn't matter. And then a bunch of other stuff, right? So the verifier will do that on their side. So they're constraining how this error is created. So the prover cannot just input anything they want as error. Okay, that might be confusing. This is really to help you if you're reading the paper. Otherwise, it's going to be more confusing than nothing. If you don't want to read that paper, or if you're only interested in the high level ideas, just remember that we're folding two instance witness together before we even prove them, and that's what's going to be useful in the next video. Okay, so hopefully, even if I lost you, you're going to get something in the next video. So I think I explained everything there is to explain here. And yeah, just rewatch that video and take a look at the paper. It's really well written if you want to understand more about what's going on here at a low level. But as a recap, we're compressing two instance witness. So instance witness is a public input and the witness vectors of Plonk together to create a single instance witness by simply taking a random linear combination of everything from the first stuff plus R times the second stuff, basically for everything. And because of things of the multiplication and cross products and everything, we have to use some tricks like this slack vector and this relaxing factor to make it work. But as long as you change the Plonk protocol to check that equation at the end, you're golden. Okay, so let's see each other at the next video where I explain how Nova makes use of that to do recursion pre-proof.